Right, so today is the day. We're actually proving the PCP theorem. Yeah, so if you've forgotten, we looked at two strengthenings of a notion of a PCP. Okay, one is robustness, one is proximity. Actually, these are orthogonal strengthenings. We'll use both of them at some point today. And the reason why we spent 2 lectures on each of these, where we basically showed how to basically white box prior constructions and that we already knew how to do and sort of obtain stronger results, it was so that today, armed with those strengthenings, we can actually go ahead and finally prove the PCP theorem that we've been writing on the whiteboard for weeks, right? And we'll do so using proof composition, okay? So before we actually do go ahead, so I want to motivate the notions of robustness and proximity, so we're actually not going to start with them. We're just going to go ahead and try to get started with proof of composition in some whatever seems to be a natural way. Then we'll see that kind of we get stuck at certain places, and then at those places, it will become clear that kind of robustness and proximity is exactly what we need. Okay, so that actually those are really natural notions. So there is one definition I need to put down before we start. Intuitively, if we're going to do kind of proofs of proofs, the kind of inner proofs, I'm going to discuss the execution of the verifier of the outer proof. Okay, and because of this, it will be convenient to have the notion that is of decision complexity. This is basically how many gates it takes to make up your mind as a PCP verifier. Okay, so we're going to define that first. Okay, so I'm going to say that a non-adaptive PCP PCP verifier has decision complexity d of n. Okay, if let's do like this. D sub x comma rho is at most d of size of x, and who is this guy? Where d sub x comma rho is the circuit that maps the queries that are queried on instance x and randomness rho to make up the decision of the verifier, and this is the circuit, the Boolean circuit, such that so we can view the verifier on input x and randomness rho as basically running this circuit on whatever the proof says at these locations. Okay, so again, we have all of today was with like pretty much every week is with non-adaptive verifiers. So I'm saying, look at the verifier. Okay, these are the queries that he's interested to look at. These are the answers. Okay, and this is how the verifier decides. Okay, they're going to say that the PCP has decision complexity d if the size of this circuit as a Boolean circuit is no more than d of x. Okay, so that's a notion. All right. Okay, so now we're going to prove a lemma, a proof composition. I'll first state it, and then we'll see where it comes from. I also put it in quotes because the lemma is false, okay? But at least it will give us the skeleton of what it is that we want to do today. Then we'll come back and fix it. So what we want to do is we're going to start out with 2 ingredients, an outer PCP, okay? And the outer PCP is going to be for some relation R, which is the one that we care about for proving. And it's going to have some parameters, so let's give them some names. L out is going to be the proof length of the outer PCP. R out is going to be the randomness complexity of the outer PCP. Q out is going to be the query complexity. Now, by the way, typically we keep track of R and Q. Sometimes just for clarity, we also add the proof. Today specifically, it will be helpful to keep track of the proof, even though it's implied by the randomness, okay? And we also have this extra measure of decision complexity. So that's why we're going to have an additional parameter here that tells me, you know, this is the decision complexity of the PCP. So all I've done so far is to say, consider a PCP for a relation R, okay? Now, the inner PCP is going to be specifically for the relation CSAT, okay? And again, I'm just going to parameterize it. It has, you know, some proof length, some randomness complexity, some query complexity, and some decision complexity, okay? What we want to do is we want to take from these and construct a composed PCP, okay, for the relation R. So R is our target, okay? The inner PCP is only going to help us compose, and we really have to target only just one thing, which is whatever the verifier of the outer PCP is saying, okay? That's why we're focusing on CSAT, because we're thinking of verifiers as Boolean circuits, okay? And we want to construct it with some parameters, okay? And now the parameters, we'll fill them in as we go along, but let's at least focus on what it is that we're trying to gain, okay? So what is ultimately our goal? Well, we have various PCP theorems that we've proved. There is the PCP theorem that we have yet to prove, okay? What is the key parameter that we're after? Yeah?
Proof size and query complexity?
Sure, yeah, exactly. So we want polynomial size and constant query complexity, okay? So kind of, we're very interested in like what will appear here, kind of the proof length, right? And, okay, so that's randomness. I mean, the same thing anyways, but you know, we really want to make sure that at some point here we write something that is constant, right? And our grand plan was to say, look, we're going to compose things so that we inherit in the composed PCP the proof size of the outer PCP, right? And the query complexity of the inner PCP. Okay, so that's what we're going to try to do, and we're going to fill it in here. Actually, let me tell you the answer so we know the plan, and then we sort of prove the actual lemma, okay? So what's going to happen is that we have to write out the outer PCP, okay? We'll write it out. But then we won't be checking it directly. We'll ask the prover to write additional information that will help us check it with the inner PCP, okay? And this will consist of basically additional proofs. How many? Well, all possible executions of the outer PCP, right? Because if we're not running the outer PCP and we're just kind of imagining in our head, right, we're going to need a proof that helps us check each of those possible executions. So here we're going to have a blow-up of 2 to the r out n, right? Does it worry us? Not really, right? Because the outer PCP is going to have logarithmic randomness. So that's, you know, whatever, polynomial. And then we're going to use the inner PCP to kind of reason about the outer PCP, right? So there's going to be some proof that we'll have for each of the executions. And now maybe just what should I write as the argument of this one? It will be on instances of what size?
The proof length size of the outer PCP?
That's a bit too large, right? So the outer PCP has, like, how do we check the outer PCP? The question is catching your head. Okay. What is the thing that we're checking? What is the computation that we're checking from the inner PCP? Yeah? Yeah, D. Which one? Which D? Yes, D out, right? So we have a problem to check, which is, does the outer PCP verifier accept or not, right? So kind of, we are running the inner PCP to reason about a circuit of this size, okay? So again, that's not a construction. Right now we're just trying to kind of imagine what would be an ideal thing, right? So then we have to see how it actually plays out. Now, in the end of all the executions of the outer PCP, we will run only one of them. So we're expanding the randomness to just decide on which execution, right? We'll not run all of them, right? We'll just pick one. For the one we pick, then we'll invoke the inner PCP to check it, right? So we'll also need to expand our in, right, of what? What's the argument? Same thing, again, the out of n, right? Because that's what the inner PCP is going to be doing, right? So it's called upon to check something of size d out of n. Okay, so we'll have a random execution of the outer one, and then we'll check that one with a random execution of the inner one. Okay? Now, the query complexity, what do we think the query complexity is going to be? But today we'll cover composition 3 times. Once is like this, basically in our head. Then we'll actually play it out, and then we'll actually prove it. Okay, so because it's not a difficult thing, but it's an important notion. That's why I'm going through it. So, how many queries do we expect? Yeah.
Shouldn't it be the constant number of queries?
Wait, there's no constants here, right? So these are the only letters we can play with. So as a function of the parameters there, what do we expect here to be? Q in of what? D out, right? So that's it. Q out of n just won't matter. Okay, now of course it matters a little bit in the sense that D out of n is at least as large as Q out of n. Because guess what? This is the size of a circuit that reads all of those queries, right? So it's not like we're cheating. It's just like we're not actually running the outer PCP. We're just checking that the execution of its verifier, or rather its decision predicate, was done correctly, okay? So we do have an implicit dependency on Q out of n, okay? But it is plugged into whatever function Q in is. In particular, if Q in is constant, this thing reduces to a constant, right? And then the decision complexity is going to be, just whatever, d in of d out of n, right? Because this is the cost to decide on instances of this size, right? Okay. So this is kind of, at high level, what we expect to happen. Now, our composition plan, I have mentioned before that to obtain the PCP theorem, one composition won't suffice. We'll actually have to compose twice, okay, twice in a row. So our first composition is going to be the LDE PCP, the polynomial size PCP with polylog query complexity. We're going to compose it with itself, okay, to get some composed PCP. Okay? Again, so this is the one with the read-molar code, with the low degree test and everything, sum check. We compose it with itself. And then we'll compose the composed PCP with the Hadamard PCP. So this is the exponential size one. Okay? And this will give us the PCP theorem. So that's the plan. Okay? Now, let's check with these parameters that these things work out. Okay? What I want to do right now is to basically take these formulas that we wrote down. We'll have to justify why they look like that, right? But right now I think we have some intuition for why they look like this, right? I want to take these formulas and carry through this composition plan and make sure that after we work through all these parameters, at the end we actually have these things. Okay? And to some extent, the interesting part is really this one, right? Like, why do we really need to compose this one with itself? Why can't we just directly apply the Hadamard, which is kind of, that's what you would want to do, right? All right. Composition number 1. So the outer PCP is going to be, let's say, for CSAT, the relation R is, the outer relation is going to be CSAT. And now let's write down these 4 parameters for the logic extension PCP. Okay? So what is the proof size for the logic extension PCP? Polynomial. And so just to distinguish bigger things from smaller things, I'll write poly of big N, okay, to mean that this is the outer thing. All right, what is the randomness? No more than log of this, right? So it's going to be order of log N. What is the query complexity? So what was the query complexity of a polynomial size PCP that we constructed? Was it constant? Yeah, it was polylog, right? Definitely not constant, otherwise we wouldn't be doing composition. Polylog of n, right? And decision complexity, truthfully, is like we didn't really look at it, right? Because back then we didn't talk about it. But realistically, it will also be polylog n, okay? And intuitively, the reason for why that's polylog n is because we're doing a efficient computation on polylog answers, right? So we're collecting polylog answers, and then we're doing something with them. And whatever that is, it will be a polynomial size computation, right? So poly of polylog n is still polylog n, right? So it's very reasonable to believe that decision complexity is polylog n, right? So polylog n. Okay. Now the inner PCP actually is going to be the same one, but I'm going to write it with the same parameters, but instead of capital N, I will use small n, okay? Because the small n is going to be this one, right, in the composition, right? So this is going to be poly small n, order log small n, polylog small n, and then polylog small n. Okay? Now, if we do the composition, what do we get? Now we have to kind of work out the parameters. So the length will be the outer PCP, so it's poly big N, right? Then 2 to the R out n, okay, so that would be 2 to the log big N, so that's plus poly n, right? Times the length of the inner one on this guy, okay? So it would be poly of polylog n, okay? Okay, but it's still poly n everything, okay? So, good. So the proof really grew. I mean, we added stuff, but it's still poly n. All right. Next, randomness is the randomness of the outer PCP, so it is log big N plus randomness of the inner PCP on the instance size of the outer PCP, on the decision complexity of the outer PCP. So it will be log of small n, which is actually log of polylog n, right? Which is log n, where n is big, okay? But you know, it's still dominated by log n, right? So I'll still just write this one, right? The query complexity, it is the inner query complexity applied to decision complexity of the outer one. So what do we have here? We have polylog small n, but guess what? Small n is this other guy, so we'll have poly log n. Okay, notice crucially we have an extra log here, okay? That's what this first composition buys us, okay? And then here in the decision complexity still again poly log n for the same reasons that somehow we are running an efficient decision predicate on a decision predicate that takes polylog n bits, okay? So the main thing that happened is that we still have polynomial size of the proof, but our query complexity and decision complexity, we had an exponential improvement, okay? Because we're not running the outer PCP, we are checking it with the inner PCP, which was actually itself ran on smaller instances, okay? Okay, is everybody happy with the first composition? Yeah?
Can we keep on self-composing it to add more logs?
It's a good question, okay? But then what's going to happen is that this thing is going to start blowing up, okay? Because you have to do it more than a constant number of times, okay?
What's the randomness in pieces across?
The proof size, really. We would need to do this, I think, log times, constant. But for the record, there are compositions that are, okay, let me put it this. It is several times the case that you have the option of 2 or 3 compositions with like well-chosen parameters, or some other composition that keep reuses the same thing, and you have to do it just maybe a super constant number of times, and you get like the similar results, or maybe the same result. This particular case, I don't think you can afford that, okay? Because your proof size will become super polynomial, but I haven't checked that, okay? What definitely is the case is the next composition will take care of it, okay? So composition number 2, but it's also a good question. Of course, it's to some extent more elegant to just pick one component and just keep improving it, right? So as our outer PCP, what are we going to pick? The thing we just produced, right? I mean, otherwise, why did we produce this new component, right? So we're going to use the outer PCP there. And why is the outer one? Because for the inner one, we finally want to, sort of pull out our exponential size PCP, which means that we have exp small n, poly small n, O of 1, and O of 1, right? By the way, just to convince ourselves that the decision complexity of the exponential size PCP is constant, well, we are running a decision predicate on a constant number of bits, okay? Remember that all we care about is the decision predicate after we have hard-coded both the instance and the randomness, okay? That's important, okay? We're just looking as a function of the number of, of the queries, okay? We have already hard-coded x and rho, okay? Both of which have super constant values. Now notice that our new n is this one here, okay? So this n here is this one, okay? The one up here was this one, right? So, but for the next composition, our new n is smaller, is poly log n, right? So in the composed PCP, we're going to get CSAT to be what? Well, we're going to have poly big N, right, plus 2 to the R out n, which is fine, right, because we have 2 to the log n, that's poly n, times, this is the inner PCP on the outer PCP decision complexity, okay? So here it says poly of poly log n. That's fine, right? So overall, we still get poly n. The randomness, well, we're running the outer one, right? So that's O of log n. And then we're also running the inner PCP on the decision complexity. And again, it's going to be poly. Sorry, before I said poly of log n, but really I meant like exp of log n. Sorry about that. And it's important. That's why. So let me say that again. In deducing this proof, right, this term was length of the inner PCP on the outer decision complexity, and that is exp, which looks scary, right? But exp on poly log n, that's fine. Okay? It's still poly n. Okay? Notice that we needed the outer composition first, the previous composition first, because exp of poly log n is not poly n, right? But exp of polylog log n, that's fine. We can absorb it, right? So this extra improvement from polylog n to polylog log n was necessary. We could not have used this one directly. Okay, so very clear with that. All right. Now coming back to the randomness, we said we had log n plus the inner randomness, which is poly n, invoked on the little n, which is polylog log n. So that's still log n. Q is constant, and D is also constant. Doesn't matter what the argument is. Okay? This is actually PCP theorem. And notice that we have followed this plan. Okay? Now, what's left to do for the rest of today is that actually we use the lemma that is false. Okay? This is not true. Okay? And we're going to have to come in, open up, and see what actually proof composition meant, because right now we've only been discussing it at a high level. And we will see that robustness and proximity play a role in this proof composition. Okay? Is that plan clear? Questions about how the parameters get computed here? Because we will not come back and recompute them again, because it's, you see, it's like pretty boring, right? This, I wanted to do it before we get into the interesting part, because then it's like even more boring, right? At least now, you know, we're happy with the parameters, and we just need to figure out a way to kind of make these parameters work out, like just for these ones, okay? Oh, it seems like everybody's in. Also, I forgot, but since today we're proving the PCP theorem, I brought some food. Like really, yeah, healthy food too. There is grapes, raspberries. These are blueberries, right? Bananas, carrots, apples, and these are mandarins or whatever they are. Like, I'm serious. Like, we should celebrate. We're proving the PCP theorem. So can you pass this around? I mean, it's been a long time, you know? Sorry for the veggie people. There is just carrots. The rest are fruits. So, like, yeah, feel free to. Okay. I mean, the class continues after today and stuff, but. The
number of times you have to repeat is log star event.
What? Sorry?
Log star event.
Ah, log star.
Yeah,
okay.
because log star is the number of times you have to take log.
But is it? Can I get by or? It's not enough. Maybe that's an exercise for to check that it's not enough to repeat this.
Log star is very, very slightly super function.
Yeah. All right. So. Okay, so how does proof composition look like? So we've done everything so far without even drawing a picture, so let's finally draw a picture of what's going on, right? So we have the outer PCP, here it is. And we have all of these potential local tests that we could be running on it. So there is a dx row 1, okay, which asks Q out queries. There is dx row 2, which also asks Q out queries. And notice that some of these queries, you know, will overlap, right? So it could be that the first test wants to look at this location, and the second test also wants to look at this location. Notice that they should read the same thing. That's important, right? And, you know, and so on and so forth, up to row 2 to the R out, right? Which also asks, you know, some Q out locations. And then the point is that Q out is too big for us. We don't want to pay for that, okay? So we ask the prover to also supply other proofs that will help us, like, not do these computations, and we supply an inner PCP for each choice of randomness, because we're going to pick one of these and run it. Okay, so now sort of we have pi inners, right? So these are all the pi inners, right? And there is pi row 1, that's a inner PCP for this guy. Pi row 2, right? Up to pi row 2 to the R out. Right, so the PCP consists of that guy and these other things, okay? Now, the candidate verifier, composed verifier, let's write it down so we can analyze it, is the following. We have V, which takes pi out and all the pi rows, X. And what will it do? Well, first it will say, okay, let me pick a random check. It will sample some randomness for the outer PCP, right? And then it will check that V pi row given dx row equals 1. Right? It says, let me pick a random check and let me check that the circuit that it can construct is satisfiable. Okay, helped using the inner PCP. Okay, so this is just an attempt, and it's actually pretty broken. So can anybody tell me what's wrong with this sort of composed verifier? This is the candidate composed verifier. Okay. What's wrong with this? So is it clear what the verifier is doing? So if it's clear what it's doing, then why is it not a good verifier? It shares locations. Well, actually makes, you're going in kind of the right direction, but sort of, for example, syntactically, what's really suspicious here? Yeah?
Isn't it checking just if the circuit is satisfied?
Yeah, and
But
really,
if it's true.
well, if it's satisfied, then it is in the language, so that's okay. But we want more. We don't want it to be whether a circuit is. So what it's checking is that it is satisfiable, right? But is that what we want? Well, what is it that we want?
The output of it?
No, this is a circuit that is it's a Boolean circuit, right? So it only has 1 bit output. Okay, so we really want to check whether it outputs 0 or 1, but not on any input. On which input?
Do we want to know the prover knows such a solution?
Yeah, but in first the prover, there's no prover. There's just proofs, right? So the answer has to do with the proofs, right? So, for example, is this verifier even looking at pi out? No. So what are we doing, right? So what we are actually interested in is that we're interested not whether this circuit dx row is satisfiable, but whether it is specifically satisfied by the restriction of pi out to those locations, right? But I could read them and then somehow incorporate them into the test here, but that's what I was trying not to do, right? So, and also it's important that across different rows, these guys are going to see consistent assignments, right? Because it could be that even when X is not in L, I might be able to individually make all of these satisfied, by some assignment. Just the assignments are not consistent with one another. Okay? So what is this pointing towards? How should I amend this construction? I need to somehow incorporate the fact that I have a pi out, and I'm specifically interested about restrictions of pi out, consistent restrictions of pi out. I'm not interested in whether this guy is satisfiable. For all I know, even if x is not in L, for every row, this thing will be satisfiable. So if that's all I'm checking, the prover will certainly be able to produce proofs that make me happy, right? So what did we do last week, like 2 weeks ago? So we need to start using some of those things, like
I want to check that whatever input proof they're using is close to pi
out. So we want to start talking about proximity, because remember, PCPs of proximity are not about being in the relation or not. It's about whether a specific witness is, say, a valid witness or close to a valid witness, right? So that was the notion of PCP of proximity, right? So we want to use proximity. We're going to make this V here is the V in. We want the inner verifier to be a PCP of proximity so that we can supply to it, okay, the restriction of pi out and ask the question, is this restriction, say, a valid witness? Not is there a valid witness, is this restriction a valid witness for this circuit, right? Okay, so, okay, problem. So all dx rows may be satisfiable even if x is not in L. And the solution is that we want to check if dx row is sat by the restriction of pi out. So how do we do it? We make the inner PCP a PCP of proximity. So the first amendment to this composed verifier is that we're gonna, well, first, like before, we're gonna sample a random test from the outer PCP, okay? And second, we're gonna check that now we have V in, because it's a PCP of proximity, it accepts a witness, right, in addition to the proof. And the witness I'm going to supply is going to be pi out restricted to Q out X row, right? I'm saying I have sampled row for the outer thing. Look at the subset of the proof that I in principle care about. Well, not in principle, but I will care about, but I'm just not going to read. This forms an oracle witness, and I'm going to have a proof of proximity for it. And this is not the X, the dx row equals 1, right? Is it clear what's happening? Now the inner PCP is a PCP of proximity. Its syntax is that it accepts a witness and a proof of proximity for that witness. And the goal of the proof of proximity is to demonstrate that the witness is close to a satisfying assignment. That witness. So here, notice that as I change row, if different circuits are interested to see the same locations, I will be supplying consistent witnesses, right? Because I'm fetching from the same place. By the way, when I'm writing this one, it's not like I'm actually reading it. I'm just kind of creating an API to access them, right? I'm not reading this location unless he wants me to, right? But when he wants me to, that's a query that I pay for. That's queuing, right? I'm not paying this full window. Okay, so let's try to analyze this and see if it works. Okay, so analysis. Also notice that kind of each proof pi rho here, while before pi rho was created to convince me that this circuit is satisfiable by some assignment, now this proof is specialized for this particular witness, right? Remember how we built a PCP of proximity. The proximity proof itself contained an encoding of the witness, right? The witness that we wanted to check against, right? Because there was a consistency check that we ran between a PCP of proximity proof and the witness. Okay, so these are specialized to these. That's why I can actually do this. Okay. 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 Let's start to argue soundness. Okay. Now, for every row, every choice of the outer PCP, every randomness choice of the outer PCP, we have really two cases. One case is that pi out of q out x comma rho, it really does satisfies dx rho. Could this happen? So analysis means like fix x not in a language, right? Now I want to show that the probability that this entire thing accepts is small, okay? Now I'm analyzing it. I'm saying for each choice of randomness, we have two cases. Either when I look at the view of the verifier, it actually makes the local check happy, the thing that we're checking with the inner PCP. This seems like it's an important thing to understand for a particular RAM. So could this happen when x is not an L? Yeah. Can it happen often? Like, what does soundness say for the outer PCP? Soundness says for the outer PCP that the verifier doesn't accept high probability. What does that mean? It means that for a small number of choices of row, if I look at the things that I'm about to read, I will have a decision circuit that accepts. But for the other ones, most choices of row, it won't. But some could be, right? So this case can happen, okay? And I want to say that when it happens, V in is not going to save us.
The issue is sort of that we're sampling V out's randomness, like rows V out's randomness. We don't get guarantees there.
No, there's no issue yet. I'm just saying that there are situations where V in doesn't help us. Okay, if we are in the bad case of a row that is sort of bad for the outer PCP, the inner PCP, it's not like it's going to save us out of this one, okay? We're invoking it to check something that is true. It's not, the soundness will not help us there, okay? So here all I want to say is that V in can't help us. Period, right? The only comfort that we have is that we know that we'll be in case one with small probability from the outer PCP's soundness, okay? But whenever we are here, we're screwed. That's it. There's nothing we can do about it, okay? We have a local view that is accepting with that specific witness. So in particular, the prover can produce a PCP of proximity that makes us accept, because what we're proving is true. Okay, the sub-claim, right? Not X's and N, right? Now, in the other case, which happens most of the time, the restriction does not satisfy dx rho. Okay, so most of the time we look at the restriction doesn't make this circuit accept. Okay, now because this case happens most of the time, we are relying on V in to do something useful for us. Okay, now we really need to say something about the inner verifier. Can the inner verifier catch this with high probability? So we have a witness that we know does not satisfy the circuit. We have a PCP proximity for it, okay? Arbitrary, the prover wrote it. Can we rely on our PCP proximity to accept with small probability? Yes or no? The answer is no, okay? Because the PCP proximity has a guarantee that is a little bit more refined than that. What is the guarantee for PCP proximity? It doesn't say that if W is not a satisfying witness. It says something else. It has a stronger hypothesis. It says if W is what? Yeah, it's far, right? And if you think about it, of course, if I have a small number of queries, that's all I can ask for, right? Like if I plan to check this with a sublinear number of queries, I can't expect to say I have an error somewhere and reject with constant probability when you have 1 out of n errors, right? So I need to have some constant distance, right? So here, we would like to say that V in saves us, but it can't. He would have to read all of this, okay, to catch this with constant probability, okay? So PCP's proximity will save us when there is a witness, provided the thing that we're checking is far from any valid witness, okay? So here, unfortunately, V in still can't help us. And now it's a problem. So here I want to say, because maybe the restriction is close to satisfying, right? So even though it's an invalid witness, it could still be very close to a valid one. And this is a problem because this happens with high probability, and we really need to do something here, okay? All right. So what's the next solution? So we need to make sure that our local views cannot be close to satisfying. Otherwise, the PCP proximity just won't help us. So how do we do that? No. Exactly. So we have PCP proximity and robustness for a reason, okay? Because they're collaborating in the composition, okay? So we need to make sure that the outer PCP, with small probability, it gives us views that are close to accepting, but with most probability mass actually induces local views that are far from accepting, so that the PCP proximity can actually reject them, okay? So solution is that the outer PCP should be robust, okay? So that with high probability, the local views are far from accepting, from satisfiable, for being satisfiable assignments, okay? Okay, so let's try again the analysis. Okay, so for every choice of random string, we have two cases. Either the local view, sometimes I call them restrictions, sometimes local views, they mean the same thing. Either local view satisfies the decision predicate dx row. In this case, what do we say? Does robustness help us here? No, like before, right? Because if when it satisfies it, right? Yeah. Or actually, really, I wanna change it a bit more. Instead of saying satisfies the x, I wanna say is close to. It's close to satisfying. Oh, today I have terrible handwriting. Close to satisfying the X row. In this case, there's nothing we can do, right? Because that was kind of the case where we were in before. The PCP proximity, both when things are satisfying or close to satisfying, can't do anything, right? So V in can't help us. Otherwise, the other case is that pi out, the local view, is far from satisfying the X row. In this case, V in will accept at most with probability, whatever, something, right? So it's going to be S in of the out, right? So the inner PCP, because it's a PCP of proximity, and because now the local view is far from satisfying, it will accept at most with probability that, whatever is the probability that it rejects, okay? It's a soundness. Now, these two branches, are we close or are we far, depend on the soundness of the outer PCP, right? So what is the probability that we are close versus what's the probability that we are far for the outer PCP? So what's this? How often are we in this branch across all rows? Yeah.
The top part happens with error V out.
Right, so we can call it S out of n, right? So the robustness of the outer PCP will say, look, with probability at most S out, it will be the case that the local view is close to accepting, which could be either literally accepting or just close to accepting, okay? And with the remaining probability mass will be on this other case, but on this case, we know we're going to accept with probability at most S in, right? So overall, the soundness error is going to be what? The overall soundness error. The sum of the two, right? I can write something a little bit better. Maybe I can say at most S out plus 1 minus S out times S in, but whatever, right? So I can just take the sum. So S out, either I'm in the first case, but it happens with a small probability, or I'm in the second case, and given that I'm in the second case, the additional randomness of V in will accept at most S in V out of n, okay? So this is the soundness error. Now, we have overlooked something, though, which is we need to make sure for the robust PCP and the PCP proximity to collaborate, we need certain parameters to match up. What are the parameters that we need to match up? So remember that robustness has this parameter that we called, sigma last time, right? And it's sigma out, right? This is robustness parameter of the outer PCP, and it says the probability that local views are sigma out close to sat is at most S out, right? The robustness parameters was quantifying how close is close with small probability, okay? And proximity was saying there was a parameter, in this case delta in, it was saying that if the distance between your candidate witness and the set of valid witnesses is at least this much, then the probability that you accept is at most S in, okay? We had these two parameters, the proximity parameter and the robustness parameter, okay? What is the relation between these that needs to hold in order for us to be able to conduct this analysis? They can't be arbitrary. There has to be a specific relation, okay? Yeah?
At least it's the case that the inner PCP takes witnesses in the same form as the output of the robust PCP?
Yeah, but we are, we are doing that here because well, you know, it's CSAT everywhere, so that's fine. So, but I mean, these as numbers, like we need something to hold, right? When here we are saying that the in will accept at most with probability this much, we are at the very least assuming that the distance of this guy to satisfying is at least delta in. Why would we believe that? Okay, yeah. Robustness to be greater than the proximity parameter. Yes, we need this, right? Because this is saying what? With probability S out n, we will be S out close. With the remaining probability, will be S out far. If S out is at least delta in, then in particular we will be delta in far. Because we're delta in far, then the PCP proximity guarantee kicks in. Okay? So this is the relation needs to hold for the composition to make sense. Okay? Now, when you actually do it for the PCP theorem, it suffices for these to be constants, and you just need to kind of make sure the constants work out. Okay? But you know, there's a lot of leeway there. All right. Now we can go back and amend the lemma to make it true. Okay. There's the questions about the analysis. This is how we do composition. Okay. Outer robust, inner proximity. You need to make sure the robustness is at least as large as the proximity parameter. Okay. So here we need to amend the lemma so that we keep taking into account what we have learned in the meantime. So now the RPCP, we want R to be a PCP of proximity, right? And you know, in here we'll have the robustness parameter. I already said proximity instead of robustness in both places. So the RPCP needs to be a robust PCP, right? And it has a certain robustness parameter, S out of n, right? The inner PCP will be a PCP of proximity with a certain proximity parameter, right? And the composed PCP will be predicated on whether S out of n is at least as large as the proximity parameter on the out of n, right? In general, the proximity parameters may be a function of n, and in such a case, then you should consider the proximity parameter on the instance on which the inner PCP is run. And then what you get is this, okay? Notice that as the picture there shows, the proof size is the outer PCP plus all the inner PCPs of proximity. We are indeed choosing a random test for the outer one, and then we're actually running a PCP of proximity. The only queries that are ever run, actually asked, are those of the PCP of proximity. And the only test we're actually running in terms of decision complexity is the inner PCP of proximity. Okay? Now, so this makes the lemma a real lemma. But we're still not quite done, are we? Yeah, that's a good question. That's what we need, right? We need to start. So, I mean, we have seen last week how to obtain a robust PCP of polynomial size, logarithmic complexity, and a PCP of proximity of polynomial size and logarithmic complexity. And that will let us obtain a PCP with these properties. Now, is this one robust? All right, we saw a way to make things robust, right? But what we saw has its own costs. In particular, if you remember, as part of so robustness was robustization and bundling, right? And one of these two steps, I think the bundling one, actually introduces a polylog cost in the number of queries. That would be bad, because now we're already at polylog log. We don't want to, again, come back to polylog, right? So the way you fix this is as follows. You can actually already start with an outer PCP, an inner PCP that is not only a PCP of proximity, but is a PCP of proximity and robust. It's a robust PCP of proximity. And now we can see that if the inner PCP is robust, then the composed PCP is also robust. We're going to see that now, okay? So that's how we're going to fix that, okay? Now, how do you get a polynomial size PCP of proximity? So a polynomial size PCP that is both robust and a PCP of proximity? That's something that we will not see. So that's actually a step that we're not seeing. And but it involves a white box combination of ideas from one lecture from last week and the other lecture from last week. They can't actually be composed in a black box way, but you just basically try to do all of that together. Okay, that sounds believable. But once you have that, then you will have a robust PCP here. We already have seen an exponential size constant query PCP of proximity, right? Because in our lecture on PCPs of proximity, we had this template, and we applied it to both the polynomial size and exponential size. In both cases, we get a PCPs of proximity. And we're done, okay? So let's see how in the composition, if the inner PCP is robust, then the composed PCP inherits that robustness, okay? Is it clear? Okay, so where do I want to do it? I'll get rid of this case. Let's do it here. Okay, suppose the inner PCP has robustness sigma in. Okay, we already know it's a PCP of proximity, it has proximity delta in, but suppose it also has robustness sigma in. The claim is that the composed PCP has robustness sigma in d out n. Okay? Basically, it's preserved completely, right? So it's the same thing just on the instance size on which it's run, right? Because the composed PCP, whenever you pass it something of n, what you're actually doing is you're running the inner PCP of something d out n, right? So it stands to reason that the robustness parameter will experience that instance size. So we don't really have to change the construction, we just need to observe what happens, okay? So any ideas? So this is, this is the, we need to argue here. So we want to say something about V in, right? Or rather, we know something about V in, and we want to say something about V. Okay? So V is the composed verifier, V. We want to argue that the local views of V with small probability are close to accepting, right? Now, what are the local views of V? What are the local views of V?
Which V are you referring to? The second V calculation, or like?
No, the sixth V. I'm kidding. No. We're arguing about the composed one, right? So we have V. Okay, so we also have V in. Okay, the inner one. We know that the inner one is robust. We want to argue that the composed V is robust. To argue that, we should at least visualize in our heads what are the local views that we're arguing about. So my question is, what are the local views of V? Are they local views of V out? Or V in, or something else?
Isn't it like one fixed view of V out plus some number of views of V in?
So that's the thing, there is no local view of V out, right? It's gone, right? V out doesn't participate anymore. We already used him, right? He's robust. He gave us his robustness. That's why we can use the PCP proximity. But his local views are gone. We don't care about them. So that was kind of my point. The composed V, its local views are precisely local views of V in on this particular invocation. Okay, for a random row, of course, right? So what's actually happening is that for some settings of row, bad things happen, right? For some settings of row, V in just doesn't know what to do. But that's okay, right? Because robustness gives us freedom. Like with small probability, bad things can happen, okay? So with probability S out N, we don't say anything about composed V, okay? But with the remaining probability, what can we say? So now we are in this case here, right? From the outer robustness, we know that these things is far from SAT. We are running V in. It's a PCP proximity, but it's also robust, okay? So therefore, we know that its local views, with what probability, with at most what probability are they close to satisfying? S in, right? That's it. So, I mean, there's not much to say other than realizing that the local views of the composed verifier are those of the inner verifier, okay? So again, think about it. The claim is that with all but probability S out plus S in, the local views of V in are far. Another way to put it is that when are they close? Well, either we had a bad choice of row, and then we say nothing, or we have a good choice of row, in which case, with at most this probability, the local views of V in will be close to satisfying. Otherwise, it'll be far, right? So, and robustness parameter is precisely whatever V in has on the instance sizes that it's called upon to decide. Okay? So it's kind of direct that it's this one, okay? Now, of course, the corresponding soundness error for this one is the one we already derived, this one, right? So overall, what we see is that kind of the probability that local views of the composed V of V are sigma in D out and close to SAT is at most S out of N plus S in D out of N. It's direct, right? This is when we pick a bad row, right? When we pick a good row, then we just inherit whatever the inner PCP was doing, okay? Because that's the one we're actually running, okay? So if we make sure that our inner PCP is robust, the composed one will just inherit it directly, okay? There's like really nothing much is going on. Is it clear? I see some people nodding, other people, I guess, anti-nodding, or is it clear? By the way, even though it's not quite needed, an interesting observation is that, I mean, it's not needed for this particular construction, but it is useful in general, is that the symmetric property is also true. That if the outer PCP is a PCP of proximity, then the composed PCP is also a PCP of proximity. This is actually a great way to construct better PCPs of proximity. Because you might wonder, oh, we just constructed a PCP for NP with polynomial size and constant query complexity. Can I do the same and construct a PCP of proximity with constant query complexity? That may be a useful tool. It is a useful tool, okay? And a good way to do that is you start with a robust PCP that is also PCP of proximity, the same thing you're using here, right? So once you've constructed this one, you can also use it here, okay? And then in the end, that will give you a PCP of proximity with constant query complexity. So that's also useful to check. So let's check that, okay? So the next claim is that if the outer PCP has proximity delta out n, then composed PCP has proximity delta out, make sure I need to get it right, delta out n, yes. Not the out n, delta out n. Why is that? Well, so first we need to change our hypothesis of soundness. Before we were saying, suppose x is not an L, right? But now, since we're going to prove something else, suppose fix any x, and suppose W is far from any satisfying assignment of x, right? From any valid witness for x, right? And then we're going to put W everywhere here, right? So we're going to say our local view is going to be a collection of queries not only to the proof, but to the proof and the witness for it, right? Because pi out now was a PCP of proximity for some witness, right? And Q out was selecting out of either of these, right? Now, with some probability, this will be, close to satisfying. With some other probability, this local view will be far from that. Okay? The end. Okay? So we have just done an analysis for arguing that the composed PCP has this proximity parameter. Okay? So again, proof composition is really elegant, okay? From a historical perspective, maybe some historical remarks, it actually took maybe more than a decade from the PCP theorem to getting to identifying, distilling sort of these two properties of proximity and robustness so they could work together in a sort of nice black box way to let you compose. The original proof of the PCP theorem in the mid-90s was actually done, it was sort of vastly more complicated because it was all white boxed, okay? Imagine all the tools we've built so far without these definitions, just constantly arguing about like the distance of things and proximities. It's a mess, okay? Now, actually, things get even better in the sense that if all we cared about was just proving the PCP theorem, there's a proof that doesn't go through via proof composition. Something called gap amplification is a non-algebraic combinatorial proof, and it uses expanders, okay? Now, the reason why we didn't cover it in this course is because the PCP theorem so far, well, I mean, it was a goal, but also just getting there, we were exposed to all kinds of notions and techniques that have found life and uses well beyond the PCP theorem, okay? So somehow, even though if I really only wanted to prove maybe the PCP theorem, maybe we don't have to talk about the Hadamard PCP, okay? But just being aware of the Hadamard PCP, has all kinds of implications to cryptography and complexity theory, sort of beyond the specific PCP theorem. But if you just want to draw a line from nothing to the PCP theorem, maybe that's worth 4 or 5 lectures as opposed to 27 lectures. And it's a different proof, okay? But still, even sticking with this proof composition, this was a major sort of achievement of systematizing and distilling the key ideas. Now we can indeed wrap up all of we've done into like nice components. We just need to start with a robust PCP of proximity of polynomial size and polynomial query complexity, and separately have a exponential size PCP of proximity with constant query complexity. Having achieved these things, we can compose them and get the PCP theorem, okay? Now what we're gonna do next, we're gonna spend 2 lectures on parallel repetition, okay? We'll motivate that next time. And then we'll, I think we'll have 4 more lectures. Still thinking what to do, but what I think will happen is we'll discuss some constructions of probabilistic proofs that actually are sort of very recent and rather efficient, and they actually have practical implications. They're sort of very nice, so clean constructions. And they sort of build upon many of the ideas we've seen so far. By the way, in the meantime, I hope you're making progress on your class project. Okay, if you have questions, do bug Nick or me. Yeah, I think that's it for today. Please take some of the food with you.